Let's see if this works. So I'll start with an example. This is from Polostek and Tversky in 1970. And the reason why I'm picking this example is Tversky is one of the very best people ever in the behavioral sciences. He died young. And this example appears in Foundation of Measurement, Volume 1, where we have great, very distinguished authors. Tversky is one, Duncan Luce is another, Pat Suppies, and Dave Krantz. Not people, if you know their work, who make very many errors. But they put this in their book. And what Polostek and Tversky wanted to do was, Clyde Coombs had sort of a theory about how people were judging risk, and they wanted to formulate the theory. So what the theory is about simple gambles, where you get A with probability B, and A with probability P, and B with probability 1 minus P in dollars, and then you give these gambles to people and they judge the risk. They gave a set of axioms about risk, and then using these axioms and the central limit theorem, they concluded that risk had to have this form if their axioms were true, where E is the expected value and V is the variance of the gamble. If you look at this, what happens is there's this parameter T that varies from subjects, and it basically says that you can assign a number to each subject about how they weight the difference between variance and expected gambles. And here's the model appeal. It's perceived risks of simple gambles increase with variance and decline with positive expectation. Individuals vary in their risk perceptions according to how they trade off. Increased variance with increased expectation, and individual variability captured by a single parameter T. Okay? Because of these conditions, T apparently has an interesting psychological interpretation. And all of these make sense, and the model captures it. Rotscombe, who was a mathematical psychologist, said, well, relabel the simple gamble as in dollars, because they wanted the gambles to be in dollars. That's how they talked about it. And the explicit outcomes of gambles. Then he gave a new notation, since he was Dutch, of moving the gambles into guilders. And so it happens you could translate each of the gambles in dollars to gamble in guilders, and then you would get, and then he takes a value of T like 0.7, which seems reasonable for maybe one person, and you get this little table that tells you how much each gamble is worth in guilders and how much each gamble is worth in dollars. And the one below, G2 is the guilder version of the dollar gamble, and at the exchange rate at the time. And the table shows the inconsistency, because the risk, according to the model of G1, is less than G3, so the subject should perceive G1 less risky than G3. But because G2 is a translation of G1 and G4 is a translation of G3, it follows that the subject should, therefore, have the risks of G2 be greater than G4. It shouldn't really depend on whether or not the gamble is in guilders or in dollars. If it does for a subject, well, that's not a very good subject, but this should also hold for bankers and other people who are interested in risk. But this is not what the table shows, so there's clearly inconsistency. Well, what's wrong is the model just doesn't make sense as a model of risk. It has all these beautiful properties that we want the subject to have. I mean, it has these nice properties, and it's a simple model. And probably if you ran experiments, you could fit parameters and it works. Even if the model we ran it in dollars worked perfectly for a set of subjects, it's still nonsense. You can have a model that fits and predicts perfectly, but that doesn't mean that it's capturing what you want it to capture, right? And this is a simple idea. You just change from guilders to dollars, and this is an example of meaningfulness. That you have some mathematical expression that's supposed to go and say something about the world, and it fits, say, your data, which even is better, but it really doesn't say anything about the world that you want it to say about the world, right? And I think Fred Roberts will have more profound examples. Well, you think that this is, well, they were a bit crazy. You can go in economics and find, without much problem, lots and lots of these things, where if you just look at it, you change currency, you get a different result. They like writing down these mathematical expressions. You do so much work, you put in so much capital, you see so much in products, you put these things together and they write down some formula. And if it isn't linear, they run into trouble. You can fix it by putting in things like dimensional constants. But look at this model. If I put dimensional constants in, God, this is such a nice model, one parameter. Now I have to start adding in other types of parameters that vary on currency, and the form of the equation is going to change. And you use that form to draw all sorts of conclusions. So that's a simple example of meaningfulness.
Just to make, there are not many economists here, but just a few years after Revisted, there was an ordinal definition of risk aversion based on sort of this sort of thing, which economists have followed since then.
Oh, I'm not disagreeing. This theory was an ordinal theory. The formula is not ordinal, but the theory was a qualitative ordinal theory about gambles with just a preference ordering on gambles. He did not write down the model, he derived the model out of ordinal considerations. After all, it was Tversky, right? I don't mean to put down economists, it's just that, it's just that, first of all, they have high status, and second of all, they're good and bad economists, right? And some of the bad economists are famous. Okay, so that's the meaningfulness. So here's an idea of quantitative meaningfulness. Goes back to Stevens. You start with a qualitative structure. Stevens didn't have that, but this idea of meaningfulness really is his idea. And S is a family of isomorphisms onto a numerical structure, and sometimes we call this family measurements. Then a relation of T is said to be quantitatively S meaningful if and only if, whenever I represent it or whenever I measure it, it doesn't matter which scale I use to measure it or which scale I use to represent it. The idea is, since these are isomorphisms, they all should give the same result. This is a type of meaningfulness that we use in measurement theory. Then we have an idea of symmetry meaningfulness, which is somewhat similar. You start with a qualitative structure, and S is a family of isomorphisms onto another structure. And then we see for each of these isomorphisms, psi and theta. Psi circles theta is a symmetry of X. It's an isomorphism of X into itself. And then for each measurement scale we have, if I take first an isomorphism, then I take the measurement, its representation or its measurement, then I get a, did I say this right? Then I get S. What?
You need something in there. You just are talking about the operation, you have to have an equality.
Equality where?
Well, somewhere to show that the diagram commutes.
Oh, that's already in this type of thing because I have the isomorphism onto, and they have inverses and everything. So n-area relation is said to be symmetry meaningful if and only if it's invariant under symmetries. So if I take and so we look at symmetry meaningful ones. Each of our primitives in our qualitative structure, by definition of symmetry, is symmetry meaningful. These are ones that are not directly in the primitives of our structure. And we believe that the idea, well, we'll go on with that. The ultimate idea is that these symmetry invariance relations are going to be particularly important in understanding what is related to this structure. And I'll make that very explicit. So if Y is a non-empty set, then this is said to be, H is said to be a transformation group if and only if H is a one-to-one functions from Y onto Y, and H with functional composition is a group. And if we have an on-n-area relation, these are just ordinary definitions out of mathematics, then R is said to be an invariant of H, or H invariant, if and only if, for all elements of Y, R is invariant under the transformations in Y. Okay, that's what this says. And if we have a subset of Y, we can say what it means for that subset to be invariant. All the elements, we know what H is defined on the elements for each transformation H. We just take H of an element for all elements, and that's H of Z. And if H of Z equals Z for all H and H, we say it's invariant. So what we can do is from invariance on Y, taking functions that map into Y, we can take it to higher order concepts, to subsets of Y, to sets of subsets of Y, and keep going up on power sets. So we can take it all the way up to any level of abstraction. And we can extend the notion of invariant. Okay? So we have higher order invariance, and that's what this does. We just proceed in the same way. So that's, then what I want to talk about is a famous program in mathematics called the Erlanger program. And as Don mentioned about some of the stuff we're doing in meaningfulness, being developed equally well in mathematics, the same thing happens here, is that the type of basic concepts we're using about symmetry and invariance was used in mathematics in the 19th century. As I'll point out, there's a real big difference because we're doing science and not mathematics. Somewhere the difference between doing science and mathematics will become apparent, or should become apparent, that there's something different about science than mathematics. And it's kind of hard to pull apart in mathematical science what the difference is. But the Erlanger program was about mathematics, and it was about analytic and synthetic approaches to geometry. A synthetic approach consists of a structure of primitives like Euclidean geometry, and these are Euclidean primitives of point, line, plane, incidence, congruence. And the analytic geometry would be sort of like giving a coordinate system, a perpendicular coordinate system, and a law for distance. And that would be analytic, and the question was, how are the analytic and synthetic geometries related? Most of us don't know how they're related. We just assume they're related. We learned about Euclid's axioms at one time, and then we go to college, and then we learn about analytic geometry. And are they really the same subject matter? I mean, they're entirely different. It's just that one thing you talk about lines as equations, and another one you talk about lines as something that has some mental kind of meaning to it. That's the synthetic aspect that the important thing in the synthetic approach. It's not any set of primitives, it's a set of primitives that have some mathematical content that all fit together. And the Erlanger program wanted to deal with the question when two geometries were related. If you had two synthetic geometries, they may have different primitives rather than using point, line, and distance. Point, line, and circle and things like that. You might had a primitive of perpendicularity. Dana Scott came up with a system where you use perpendicularity. Tarski has systems where you just had an idea in three space, some sort of ball. And then you have one ball containing another ball. There's all sorts of primitives that you can give. And when do you say they give the same Euclidean geometry? Well, for one set of primitives, you can define the basic concepts of the other set of primitives and show that in these definitional ones, all the axioms held of the second set. Then you can say the first set somehow implied the second set, and the second set implied the first set. But what happens if you couldn't define things? Not everything is necessarily easily definable. How do you do it? Well, the Erlanger program was designed to do this. Also designed to say when you have coordinate geometries and synthetic geometries, which are really about quite different things, when they were the same. So the Erlanger program, which is one of the great ideas of mathematics, identifies geometries with transformation groups. So two geometric structures, either synthetic or analytic, are said to specify the same geometry if and only if they have isomorphic transformation groups. All the mathematical content of the geometry is being given theoretically by this program in the transformation group. You understand the transformation group, you understand the geometry. And the Erlanger program led to a revolution in geometry. All these people worked on it, and they basically exhausted the field, and we no longer, in American universities, teach geometry, at least that type of geometry. They just exhausted it. But what they went and they would find a transformation group, someone would come up with, and then some clever person would think of a synthetic way of giving axioms for that transformation group. And the better the mathematician was, the better the synthetic axioms were, the more like geometry it was. Okay, so that's the Erlanger program. Okay, would I go forward? Okay.
Symmetry group is what you're going to get to next.
Okay, so I have to go back. Okay, so I think I said enough about that. Okay, the axioms, when they axiomatize groups, well, in the Erlanger program, the role of the axioms is to specify the group theoretic properties of H up to an isomorphism. That is, two axiomatic structures describing the same geometry will have isomorphic symmetry groups by the Erlanger program. Okay? And this is just a summary. A geometry is a transformation group. All of a sudden it becomes very abstract. Now it's a transformation group on a non-empty set. The relations, all higher order ones, they're invariant under H, belong to the geometry. Those that are not invariant don't belong to the geometry. So we have the Euclidean transformations, something that's not part of the Euclidean transformations, non-invariant under it, are not Euclidean, even though you can write down this equation in Cartesian coordinates. Okay, so there are two big gaps in the Erlanger program. And the first one, I could not find any coherent even discussion of it in the mathematics literature, starting from the 1800s up till present. It is, why should invariance belong to Y? Why should this work? It works. That was its power. The Erlanger program and all this works and works and works and gives the right answers all the time. Why should invariance belong to the content? Why is you identifying content with invariance? The second problem was the case of having a trivial group, so you only have the identity. Under the identity, everything is invariant. And that presented a problem. That Klein had to confront because you had Riemannian geometries that only had the trivial group, and Klein's response to this was, they're not geometries. He left it at that. And the people who were doing differential geometries were insisting they were just as good synthetically, whatever, but Klein ruled them out. What happened historically was later Einstein's special theory of relativity came in, and they discovered the transformation groups, the Lorentz groups, and this was a great victory for the Erlanger program. And then Einstein's general theory of relativity came in, and there was only one. You only had the identity as isomorphism. This was hard to swallow because you can't really deny that physical space is not a geometry. And people tried to fix it. Eli Cartan is the most famous, or the best mathematician, tried to fix it by generalizing the idea of morphisms. But when you generalize the idea of morphisms, you really lose the idea of content. And that runs into problems, particularly if you look at higher order content. You start to lose a lot. So there were lots of attempts to resurrect the Erlanger program after the philosophical side of the Erlanger program, after the general theory of relativity. And then by 1930, it just died out. And then there have been other attempts, but they really don't work. This is what has to do with measurement theory. Measurement theory is a representational theory about how you create scales and map things in. But it's basically the idea that qualitative structure in a measurement theory, these are our empirical primitives. If we're doing science, corresponds to synthetic geometry. Our numerical structure, how we assign numbers to qualitative entities, is like an analytical geometrical structure, setting up a coordinate system, essentially. Representation, how we measure things, is to preserve structural properties, corresponds to isomorphism. And now representationally meaningful corresponds to belonging to the geometry under consideration. Okay. One big difference is concern with science and empirical matters, and is in measurement theory, and in the Erlanger program, it's with mathematics and geometrical matters. And you see that science is not really geometry. This is the first thing that we will look at in solving this problem. We also will solve the problem about the single isomorphism. Okay, so I have a half hour. So I'll go real quick now. Luce presented a theory. So now we'll go to possible psychophysical laws that several of us in this room has worked on. And I'll just say it's a field with enormous amount of promise and applications. And I think the three of us who worked on it in this room, maybe four, Jeff, will agree we just scratched the surface as far as what could ultimately will come out of it. Luce in 1959 presented a theory that was intended to generalize dimensional analysis of physics to a wider range of scientific phenomena. I'll give an example of dimensional analysis in a moment. particularly to the phenomena of psychophysics. This theory became known as the possible psychophysical laws, and it's generated considerable literature. And this is how it got started. Stevens, who was a prominent psychologist from the 1930s to the 1960s at Harvard, in a well-known article, The Power Law, provided a measurement theory and much data that psychological magnitudes of physical stimuli were related to psychological stimuli by a power law. That is, a perceived psychological magnitude, psi of x, of a stimulus x, whose measurement, when measured on a standard physical scale, is where this is the standard physical measurement, phi of x, is related by a power law. And that's what Stevens spent a great deal of time showing. Because the way Stevens carried out his experiments, his theory of measurement, when you do experiments, you're assigning numbers. In this case, you have a theory of measurement. Stevens had his own theory of measurement. His own theory of measurement required psi to be a ratio scale because he had subjects judge ratios, so he wrote down those ratios, and that turns out to give a ratio scale, and Stevens recognized that. So Luce wanted to know why we got the power law, and he wanted to do a type of derivation that's more like the type of derivations done in physics. So he made the following assumption, that each ratio transformation of the physical scale, of the physical measurement, led to a ratio transformation, h of k, of the perceived psychological measurement, and showed that this implied the power law. So he showed how psychological scales were naturally related, compatible to physical scales was enough to get the power law. And he noted the striking relationship to the way he derived his result to dimensional analysis in physics. And then what he said, well, there was something wrong with Stevens, because when estimating ratios are not ratios necessarily, so maybe the subject doesn't have a ratio scale. He didn't use Stevens' data or his idea that they were ratios. He just said that the subject had a ratio scale and was compatible. But maybe a subject had an interval scale or whatever. So he went through the type of scales that were known at the time. And so you have ratio scales, the independent variable, dependent variable, dependent variable, ratio, that was the case. We looked at here, you get this sort of equation. You can have the independent variable be a ratio scale, and then the dependent variable, in this case would be the perceived one, an interval scale. He looked at all possible mathematical relationships between these scales, and he used his method about that compatibility relation to get these functional equations. And then he tried to give, or he gave, a sort of epistemological justification of his principle. This led to a generalization of Luce's method, and I can't go into detail in it, but here's a set of people who generalize. When you're actually, the flaw with Luce's method, if you're actually going to apply it to experimental psychology, is you're making an assumption about the scale type of the person that you can't see. And you would like to replace that assumption by things that you can see that are very simple, like comparisons of certain orderings. And this was done in all of these papers. They have got rid of that one. They got the mathematics essentially better. Ultimately, they got the mathematics very well in these papers with Excel. So that was one sort of thing. You can also generalize it to many variables. All of these papers did this. And then you could generalize the notion of a law. Luce had there was a single function that related things. But that is very, very constraining. There's often a set of functions because you have dimensional considerations that go on if you have many variables. And that was looked at by Jean-Claude and me. But anyway, here's a part of the literature. Jean-Claude will continue with it. I like to note this particular paper, which tell you about how you can aggregate data and all sorts of meaningfulness problems in aggregating data together. That was sort of the last paper, I think, on aggregation I know about. And then this paper on Jean-Claude that appears in Foundations of Physics, where he demonstrates that this method has quite a lot of type of power and can explain unusual physical laws. Not just things out of classical physics that you're quite aware of. Okay, so here's an example of dimensional analysis. Consider a simple pendulum consisting of balls suspended by a string, and you know it's this place, and you release the ball and it swings back and forth. You want to find the period. And by dimensional analysis, you do this by a list of the relevant physical entities that determine the period. In this case, it's the mass of the ball, the distance of the string, the gravitational constant g, and the angle you start with the pendulum. If we take the relevant, so these you might think as your axioms or qualitative structure. If we actually measured things, we would have a measurement scale for mass, a measurement scale, and a bunch of axioms about how you measure mass, a bunch of axioms how you measure distance. The gravitational constant, we would take a number for, or we just leave it there as a theory part. But let's say we take an experimentally determined number, and you have the angle, which you have a measurement theory for angle. And you look at these and you say, that's all that I really need, that whatever physics is going to do, this is enough to actually specify what the law is. Obviously, if I took certain things away, like the mass, or I don't know, if I took distance away, you wouldn't be able to, I didn't tell you how long the string was, you wouldn't be able to tell me what the period is. Okay, so by doing dimensional analysis, which I don't go into, you end up with this formula where k is a non-negative constant, and you haven't used any Newtonian physics. You only use measurement. If you use Newton's laws, you get a bit more. So it's good to know that Newton's laws give you something here. You find out that k is the sine of t. But if you're an experimentalist, you just, you know, you measure d, you know what g is, you measure t, you can find what k is. You can solve for k. So you run one experiment, and you know, that's good enough. You don't know exactly the sign or why the sign. So that's dimensional analysis, enormously useful in physics. This is just sort of like a toy example compared to what you do in physics, and it's the basis of things like the wind tunnel and how you test in ship hulls and all sorts of things like that. They do it through dimensional analysis. So a theorem, what Luce did was in 1978, he axiomatically formulated what dimensional analysis was for classical physics by measuring all the variables and putting all the stuff in, taking the principles that they used to draw inferences in dimensional analysis. He put it all in axioms, and he showed that it satisfied the conditions of the Erlanger program. He didn't quite say the Erlanger program because I don't think he was quite familiar with it, but this is what he showed. So dimensional analysis was the Erlanger program. It is what he originally had in mind when he did his possible psychophysical laws, and meaningfulness comes out as sort of a natural type of thing. So now I'm going to go and take that tricky thing about the Erlanger program, but it's going to be different because we're talking about science. I'm going to give some principles about what a scientific topic is. Okay? And the idea of scientific topic will be in the Erlanger program what you call or would be called the geometrical content. So if we took Euclidean geometry as our scientific topic, it would mean what is Euclidean versus non-Euclidean. If we are doing something mathematical, like in an analytic geometry, where we can write down any sort of formula we want using derivatives and whatever, which curves belong to Euclidean geometry and which don't. Classic problem that went back to Plato. So the domain of a scientific topic is a qualitative set X. That's the first principle. Second principle, that makes sense. Qualitative means it's not going to be numbers. The scientific topic is determined by a structure of primitives, where each primitive is a higher order relation based on X. So it's either X, a subset of X, a binary, 3-array, 4-array relation, a set of relations on X, and so forth, going on forever. That's the second principle. And this is very similar to the Erlanger program of what synthetic geometry is. The structure of primitives, and each of its primitives belongs to a scientific topic. So we're only axiomatizing our scientific topic into things that belong to it. And that's part of the Erlanger program. Principle 4, the scientific topic is closed under, now here's the whole key, scientific definition. I haven't defined what that is, but I will. That is, if B1 up to Bn belongs to the topic, and B is defined scientifically in terms of B1 up to Bn, then B belongs to the scientific topic. Okay? I have to say what defined scientifically is, but we'll get to that. And the principle 5 is a portion of pure mathematics can be used in scientific definitions. So when we say we have a bunch of data, which is all qualitative, and we measure it, we get numbers, and then we take the mean of it. Well, we're doing an arithmetic operation to take the mean. The mean may not be any one of our objects. We may not even be able to identify something, but it belongs to our scientific topic. This part here about the portion of pure mathematics is sort of way this part of the thing differs from philosophical definitions of philosophical ideas of, well, what it means to define something. It has a little bit different property. Now, the scientific things, several things have to be specified. The primitives are one thing about how you specify those. That will take us non-problematic for a moment. The scientific, closed under scientific definition, well, you can define things in lots of ways. In mathematics, you can apparently use anything to define, right? But if you want to stay in science, you might have philosophy of science things that say, well, the axiom of choice isn't right. We shouldn't use the axiom of choice for finding a physical law about physical things. We can use the axiom of choice about mathematical things because mathematics is not physics. That'd be one sort of thing. We might use very powerful abstract languages, but then we might think, well, science is empirical. We should keep close somehow to empirical reality and what's empirical. Then we just can't use any sort of formula because we're using a formula if we actually interpret it. For all x, there exists a y. How do we find the y? It's just there magically because, right? So we want to be empirical. So there is a philosophy of science that goes on that tells you what your scientific topic is. Change your philosophy of science, you change your idea of scientific topic. So I can't say what is the right one. It depends on someone's philosophy. A portion of pure mathematics can be used in scientific definitions. Well, how much? Well, the integers are nice. It's nice to be able to count things. You know, rationals, probably. Real numbers, maybe questionable. They're a bit abstract.
What's an example of what cannot be used?
What cannot be used? um, a high level of infinity. You might use a very high level of infinity. High level, I mean, not like the real numbers or power set or power set. I mean, way, way up there.
Very few
to actually,
integers.
to actually derive something that has empirical content.
Oh,
You might think that is
but you said we can use the integers, and
right.
Weyl's proof of Fermat's last theorem is about integers, but includes theories based on high levels of infinity. So how do you stop?
Take it as an axiom. It's only about the integers, right? It's weaker than the high level of infinity. As a matter of fact, there's certain types of theorems that tell you if you use analysis and all these other things, you can find the equivalent theorem in second order arithmetic. So there's all sorts of logicians have all sorts of theorems that let you. So if you use these high cardinals and you prove something about arithmetic, well, for example, if you use the continuum hypothesis to get a theorem of arithmetic, you can get the theorem of arithmetic without the continuum hypothesis. That's a known result. Okay? Well, there's sort of an interesting thing. I'm going to make sure I could try to finish the time. A kind of interesting thing is the axiom of choice, the way I said it. Bertrand Russell was a great believer in the axiom of choice, and then when the idea came up to physics, he said, of course we can use it in physics. And then he flipped and said, no, because, you know, the paradoxes of Tarski and Hausdorff and so forth. Then he flipped and said, no, we can't use the axiom of choice, but of course it's right for mathematics. The ontology for mathematics and what is allowed for science is rather different. Science is just different than mathematics. So it might be okay to use it in mathematics, according to Russell. At one point, he flipped again because Ramsey said, you just can't do that. You can't be, you have to be consistent. If it's right everywhere. It's a matter of logic, the axiom of choice for Ramsey. And if it's right for mathematics, it has to be right for physics. If it's right for, and so forth. So this is a portion. Well, by restricting the portion, some people might say, we should only deal with stuff that are computable. I had grant reviewers say that for NSF grants. So this is up to grabs. Harvey Freeman spends a good deal of his time, or did in the past, about which portions of pure mathematics gives you, which sorts of mathematics is useful. And it's a very interesting topic, but your philosophy of science also depends on your philosophy of mathematics. You just can't automatically assume mathematics is there, because then you're assuming of taking a philosophical position about the nature of mathematical entities and all sorts of things, which is highly incompatible with a lot of scientific ideas. Anyway, that's what a scientific topic is. I'll give you one. So obviously there's lots of different ways of combining how much mathematics you use and how powerful your scientific language is going to be, and concerns about empiricalness and things like that gives rise to different ideas of a scientific topic. But I'll give you one which is called the full scientific topic. You have a structure of primitives for mathematics. We could do mathematics in this as well. You just think well, just think of this being, rather than mathematics, let's make it space-time. Portion of mathematics, all pure mathematics. This is to say you can use any mathematics you want and bring it in. Language for scientific definitions. You use an infinitary higher order logic, Principia Mathematica, with constant symbols for x in each primitive, and each pure mathematical entity, or formulas of set theory, with X being a set of atoms, non-sets. This is how Zermelo originally formulated set theory, and constant symbols for each of the set X, each primitive, and for each pure set, for each mathematical entity. So you have an enormously large, powerful, infantry language to describe everything, right? Although we can describe it in a meta-language very shortly, like I did. And then you get this theorem. If a higher order relation R based on X belongs to the scientific topic determined by X, if and only if it's invariant under the symmetries of X. And this is the Erlanger program. So the scientific topic agrees with the Erlanger program when we use very powerful languages and assume all of mathematics. And the conclusion is the Erlanger program is general. So if we want to generalize the Erlanger program, we can't generalize it by going to homomorphisms or other types of morphisms. It just doesn't work. The algebraic method doesn't work. But this definitional method does work because we can either weaken the language for scientific definition, and then we will only get a portion of the Erlanger program, or we can get it by allowing a smaller portion of pure mathematics to be used for defining a scientific topic. For example, just the integers, or both 1 and 2. Okay? In this case, the theorem becomes, if we make this generalization, if the higher order relation based on X belongs to the scientific topic determined by X, then it's invariant under the symmetries of X. So here we're relating a definitional concept, scientific topic, to invariant, and we'll show how to use that in a second. So here's the use of it. So consider the situation whereby extra scientific means, intuition, experience, etc., a scientist is led to believe that a function, z of f of x and y, that he needs to describe from a subset of the Cartesian product. So it's not only a Cartesian product, it's some subset. Into x is completely determined by the observable first-order relations on x. In the example of the pendulum, it would fall into this situation where x would be consist of all possible lengths, all possible physical times, all possible angles, etc. Okay, and the first order relations would be our measurement relations, how we measured each of those things. Then it's reasonable for the scientist to proceed under the hypothesis that f belongs to the scientific topic, right? You have this function, and if this is enough to determine what it is you're talking about, and I know that this function I have really belongs to physics, and if I have correctly determined everything, correctly determined all the relevant variables. Of course, if I don't have all the variables, I'm in trouble. But then it belongs to the scientific topic, which for this discussion can be taken for the full scientific topic. Thus, the scientists assume f has a scientific definition in terms of x and primitives. By the previous theorem, f is invariant under the symmetries of x. Right? So now we know we didn't use the idea of symmetry anywhere here. We just used the idea that we understood what the relevant variables were and that we had this function. And it was about the scientific topic. Then we know that it's an invariant. Okay? Suppose he knows enough about the properties of x, those are the primitives, and has a mathematical scale to determine the symmetry group of x. And by methods of analysis involving symmetries may be employed to derive information in characterizing X. There are several ways in the literature of doing this. One way is functional equations. There's other ways that we have, several of us have developed for doing this. Note by this is important. Here's our epistemological principle. I'll be finished on time. Don't worry. I'll even finish a minute early. Note that in the above process, scientific definability is used to justify F belonging to the appropriate topic. That's what it is. It's the justification. And variance is used as a mathematical technique. After all, definability is not very interesting mathematics. Generally, logic, except for a few parts of it, is rather boring, not very interesting, boring mathematically. Not very interesting mathematically, but invariance and group theory, of course, is very interesting mathematically, and it's a powerful technique. We have a lot of mathematics for finding information about characterizing F, and that these two uses are connected by a theorem of mathematical logic. We connect the two. Okay. Also note that the science belief that F belongs to the topic is generated by a topic generated by X is extra scientific. It's not part of science. It's part of, therefore, the deductions based on the information obtained through the process should be either checked by experiment or derived from accepted scientific theory or facts. They should be treated as scientific hypotheses that need corroboration, right? Because we assume that there was a scientific topic and all these things belong to it, and it's about our beliefs. And so what this does, what's the useful is, it doesn't tell us that this really is going to hold scientifically. What it tells us is exactly what to look for. We didn't know anything about F before except what was related and belonged to the topic. The group theory part tells us a lot about its mathematical form, right? In particular, it tells us a whole bunch of things that F cannot be. Those things that are not invariant. Sometimes that tells us exactly what the formula is. If not, it tells us a very small, focused set of formulas to look at for F. Okay, so conclusion about the example. For purposes of science, the above process is a method of generating hypotheses and not facts. If the extra scientific beliefs are correct, then the generated hypotheses will be facts. However, the scientist has no scientific guarantee that his beliefs are correct. The one automorphism case is just taken care of by weakening the definability conditions and then demonstrating that you get some good results. I don't have time to do that one. Finished. Thank you.
There's one glaring absence that we saw in this talk at this conference, and that is Jonas Axel is not here. He wanted to be here, but for reasons, for those of us who know Jonas, understand he was unable to, but he does send his warm greetings to Jean-Claude. Comments, questions?
Yes.
A couple of slides back, you say that, there's a few more. You say that you have two choices for the scientific definition. You either have to weaken the language, which allows you seemingly to do scientific definition that is not strictly mathematical, or you will always be mathematical, since mathematics are just symbols and language. Is this where you can get to descriptions that are good but are not correct, or?
If you weaken it, then what happens is you have fewer descriptions. The problem with the Erlanger program, with the full scientific content is that everything is meaningful. When you weaken the language, what happens in this case is you start to get richer groups of transformations.
Another way to put it is it necessary in order to do science to have this option?
No, you could do science as mathematics, right? It's in law of science is in the physical department. I wouldn't suggest doing social science as mathematics, though.
Well, that gets to an important point that I stated earlier. I don't think we really truly understand the type of mathematics that needs to be done to fully handle the social sciences. Rain Takapeta has a book on Rain about some of the ways in which it is being done. And several of us here worry about the way in which the mathematical models, various things crop up. In fact, that's this point that Fred Roberts and I will be discussing next week. And it is an issue of, you see, what happens is the physical sciences and mathematics really enjoy a wonderful symbiotic relationship for a couple of millennia. Advances in one area led to discoveries in the other area. And so a large amount of the mathematics which we see today is mathematics that comes from the physical sciences. It doesn't take long to realize that the physical sciences and the social sciences are not the same. And yet the mathematics we're using to try to understand the social sciences satisfy the different conditions that Lewis talked about, etc., coming from the physical sciences. And I think a wonderful, wonderful challenge is to better understand what types of mathematics. Can we create the types of mathematics? Can we create some of those issues to handle in a much more realistic and meaningful way the issues of the social and behavioral sciences? And that's one of the reasons I happen to really like the area of meaningfulness, because it's one way, not the only, but it is one way to really try to capture some of these notions.
So
I don't know what's going to happen. Of course, it's research is done.
So, for example, on some of the weakening of languages, there'll be a different type of group-like concept. Groups won't work. To actually use the weakening language effectively, you need to develop a new mathematical concept that corresponds to the type of invariance that our language or our theory is telling you. So this is something that wouldn't come out of physics, or it might, but it hasn't, but it would obviously come out of something like this. Because the weakening language doesn't get at it. That just gets the weakening, this gets a better philosophical foundation. But we want our foundation to yield something, to yield some sort of substantive conclusions. This not just be a better formulation. To that, we need something like group theory. But the morphisms don't work. So mathematicians will have to come up with a way of making this into a useful theory. And there will be invariance. I have demonstrated that there are other invariance concepts that matches some of these things.
Mathematicians, I think mathematicians working with the social behavioral scientists, I don't think you can count on one group alone.
Yeah.
If you do, I'd be very leery of anything that comes out of it.
But we can say what the problem is.
Oh yes, and I think about working
Yeah.
together on it.
Yeah.
One of the mathematicians who has worked with social and behavioral sciences and found some of the results that we saw a long list of them, is Fred Roberts, and we'll hear him next. I suggest we thank our speaker now, has some personal comments with Lewis, and then we'll meet in about 15 minutes.